Good afternoon. Welcome to the final tutorial, SQAB, and it's my pleasure to introduce Joe Myerson, Washington University, who will be talking to you about cognitive aging, a behavior-theoretic approach. And rather than go into detail and waste time, I will simply turn this over to Joe.
Okay, yeah, so I'm going to talk about cognitive aging, which is a little bit of a strange topic probably for SQAB. So,
Joel, use the microphone.
Okay, now is that better? We're working now? Okay. So knowing that this is a little bit of a strange topic, I thought maybe it might help to actually do a little fading kind of systematic desensitization as we kind of introduce this thing. But really, for the purposes of this talk, you can think of cognitive aging it's a topic. One could also think of it as a process or processes, but here it's just a topic that's got subtopics. It refers to age-related declines in processing speed, what's called working memory, and various higher-order abilities like learning, particularly complex learning, and reasoning. And I'm just going to kind of walk through these topics in that order. And the order actually will turn out to make sense because it makes two kinds of sense. One is that just in a personal historical sense, this is kind of the order in which we've been studying these things, but also it's a hypothesis that we hypothesize that it is in fact changes in the speed with which people can do things that affects their working memory, that ultimately then affects their ability to learn and their ability to reason. And that all these things then are, in some sense, triggered by aging. Speed can be a sensitive topic, so we'll quickly move on. And one of the reasons why we began with studying slowing, which is what happens with age, is because it's probably the most pronounced change that you see as people get older. The graph here, is looking at changes as a function of age as people get older, starting with younger adults around 30 in this study. And the dashed line shows how precipitously speed changes. And so it's dropping quite rapidly. Other abilities are relatively well preserved, so vocabulary hardly changes at all. And in fact, sometimes it increases. But other things show kind of intermediate levels of change, and these are the other things that we're going to be talking about. Working memory. In this case, we're going to be talking about a particular kind of learning, three-term learning, that actually has its origins in operant conditioning, and on to what people call fluid intelligence. So one of the reasons for focusing on speed is because it's so pronounced, but it's not just the degree of decline that's pronounced. In fact, it's also pronounced in the sense that it's ubiquitous. That is, that you see it on any kind of task that you give people to do. That older people do those tasks more slowly. It's universal. We're kind of running through use here, but use guys is all going to get slower. So it's universal in that sense. And one of the big questions has been the extent to which it's not just ubiquitous and universal, but also uniform. That is, does slowing occur to the same degree on all different kinds of things? Or are some things much more sensitive to age than others? And is it uniform as you look across different kinds of tasks? And as a separate question, if you look at the behavior of individuals, is it uniform within an individual? When an individual gets slower, do they get slower at everything? Slowing is also important because, as Salthouse has pointed out, it tends to affect other things. It's not just that you do them more slowly. One of the problems that one has sometimes in the real world is that you can't control the rate at which things are happening around you. I mean, you can contrast listening comprehension with reading, for example. You can, if your reading gets slower, you just read more slowly. If your ability to follow what people are saying, it gets slower. Okay, then you begin to lose things because they tend to continue to talk at about the same rate that they've always talked, or even maybe a little bit faster. I don't know. So that's one kind of problem, and that's what Salthouse referred to as a limited time kind of mechanism. That when you can't control the rate, you have only a certain limited amount of time in which to gather information, and if you're slow, you may not be able to keep up. Another kind of problem arises when you have to do some form of kind of multitasking, where you have to coordinate different things that you're doing. One example of how slowing gets disruptive in that case is, of course, if you take too long to do one task, you may forget what you're doing on the other task, or lose your place. So lots of behaviors, and particularly complex behaviors, are very sensitive to the speed at which people can do things, and so slowing has all these secondary consequences for all kinds of other behaviors. Cognitive aging entered the psychology of aging shortly after it probably got started in experimental psychology, and it did it in a particular way. There was a research program in cognitive psychology called componential analysis, in which people are trying to find the kind of elements of mental processes, trying to break things down into components, little different kinds of processing components. And chronometric analysis was one particular approach to componential analysis. And it was the notion that if you could measure the speed with which things were done, then you could perhaps use speed or the time that different things took as a way to get everything on the same kind of metric, and use that as an aid then in analyzing things and taking them apart. And the goal, as this kind of came into the psychology of aging, was to isolate the age-related cognitive deficits. Clearly, there are changes in people's ability to do things as they get older, and the idea was, well, can we find what the source of those things is? And, is there some particular kind of process that people aren't good at that then has all these kinds of secondary consequences? The problem, as people tried to work through this research program, is that they began to turn up more deficits than they had data. And let me give you some examples that actually, most of these examples are going to come, for the moment at least, from one experiment that we did in order to kind of look at all these things at once and see how they were related. So we took just standard cognitive tasks, things that cognitive psychologists were using. And so one thing, just by the name of it, it's clearly very cognitive. It's mental rotation. But really all you're doing is you're showing people letters that are not upright. They can be either just a regular letter or a backwards letter. And the question that you ask people is, would this letter be facing the right way if it were upright? Okay, and so you look at it and you say, no, it's backwards. Okay, the amount of time it takes you to make that decision depends on how far off the upright it is when we show it to you. And now we can give this kind of task to both younger and older adults, and see how they do, and see in particular, because we're using this kind of chronometric approach, see how long it takes them to make these decisions. So we vary the angle at which this thing is appearing, and you can see that even when that angle is 0, that is, the thing is upright, older adults take longer than the young adults. But the difference in their response times gets greater and greater as the letter gets initially further, it is presented at a greater angle from the upright position. So people would take data like this and they'd put it into an analysis of variance, and they would get an age by angle interaction, and they'd say, aha, we've found a deficit. Older adults have an image manipulation deficit because the degree to which they're slower keeps getting worse as they have to do more of this manipulation of their mental image of the letter. Here's another kind of standard cognitive task. This is called a visual search task. It's actually a conjunction search task where you're supposed to find the turquoise circle among the turquoise squares and green circles. Okay? So you can find it there, and if you're younger, you'll find it faster. And in this kind of task, in a way that's sort of analogous to what people did with the mental rotation, where you vary the angle, here you can vary the number of elements there are in the array. And the more elements there are in the array, the longer it's going to take you to find it. Also, sometimes the target really is there, and sometimes it's not. This is what data from that kind of task looks like. Again, when the set size is small, there's still a difference. The old take longer than the young do. If we go to a larger set size, again, the age difference increases. But another thing also affects the age difference here, and that's whether the target is present or not. So when the target is present, the difference is smaller at the same set size than when it's absent. So people, again, take this data and they put it into ANOVA, and they find now they've got a age by set size by target presence or absent interaction, and now they say, aha, older adults have two deficits. Okay, one, they've got a selection attention deficit because the age difference gets bigger the more distracting elements there are in that array. But they also seem to be showing what they would call over-cautiousness, because they figure that the reason why you get a bigger age difference when the target is absent than when it's present is because older adults, were going back to double check to make sure that there really wasn't a target there. Okay? So we've done two tasks, we've got three deficits. Here's the third task, and naturally a fourth deficit will emerge. This is an abstract matching task at 4 different levels of difficulty. Again, you kind of get a theme here that you take these tasks and you complicate them and see what happens to age differences. In this task, you're supposed to report which of the two top patterns is more like the bottom one. Okay? As we increase the level of complexity of the problem, again, the age difference is getting bigger. Okay? And we get this age by complexity interaction in our ANOVA, and we assume, okay, older adults are having this kind of abstract reasoning deficit, in addition to all their other problems. In fact, people pointed out that there really does seem to be a theme here. And the theme is what they call a kind of complexity effect. It looks as if almost anything that you do that makes things more difficult increases the size of the age difference. Well, that's a very qualitative kind of statement about things. And our hope was that we could make a much more precise kind of statement about what was going on. And we turned to what are called Brinley plots after a guy named Jack Brinley who introduced them, published one study, and the technique was dropped until it was actually it was revived by a student of Dick Herrnstein's, John Cirilla, who, if anybody knows about pigeon pattern recognition, may recall the name. But he got interested in cognitive aging. And he used this kind of a plot where what you do is you take a particular condition, and let's say you've got experimental condition, you've got two groups. One group's performance goes on the x-axis, and the other group's behavior in the same condition goes on the y-axis. Here is one that it's the same kind of thing that recently appeared in the New York Times, but it illustrates the principle. Each dot comes from a job category. And so what you can take for that job category, you can take the men's wage, and that gives you your x value, and find what the women's wage is in the same category, and that gives you the y value. This, like in a kind of matching plot, that diagonal is the equality line. So if wages were equal, points would be along that line. If they're below it, now women's wages are some proportion of men's wages. If they were earning more, the points would be up here. And the slope of the line defines the proportion, in this case of wages. This unfortunate point is for professors and other post-secondary academic professions. But when you do the same kind of thing with the data that this is just the same data that we were looking at before, okay? These are response times, the same three tasks, the visual search, the mental rotation, the abstract matching task. For each condition, we take the young group's mean RT and the, actually this is not the old, this is this is the average for the older group, okay, plotted here as a function of the young group's response times in the same condition. And you can see that despite all these deficits that we're turning up, there's really only one thing going on. The if you subtract a little bit here for some kind of sensory motor part that involves pressing the buttons or whatever that people are doing to indicate their decisions, it's taking older adults about 2.5 times as long as the young adults to do whatever is involved in any one of these tasks, in any one of these conditions. As anything that we do that makes it take the young adults a little bit longer, it takes the older adults 2.5 times longer than that to perform the task. So this suggests that really what we have is this kind of uniform slowing. I mean, it's also ubiquitous in that it's turning up on all these tasks, but it's to virtually the same degree here. Now, this is uniform slowing within individuals. Here is somebody who's typical. That is, they look like the group averages. But here's somebody who's really slow. Again, all their points are falling along one line, which indicates that, they're taking some fixed proportion longer to do all these different things. here's somebody who's actually the fastest older adult in the whole study. But again, they're faster at absolutely every. I mean, they're still slower than the average young adult on all of these tasks. They do. Here is one case where you do see a little bit of a strength. You know, these kinds of things show no strengths and weaknesses that are kind of task specific. Whatever is happening seems to be affecting all these tasks uniformly. This may be, I believe this is a male, and there is a gender difference in mental rotation, and that may be responsible for that if we were plotting them not against the young group but against the females, just the males from the young group. In fact, their points would probably all fall along the same line. Okay, that's one illustrative study that in fact was done to be illustrative. But here is data that's taken from 13 studies that for the most part were done to prove the opposite kind of point. That is, these were people who were trying to isolate an age difference. But about half of them come from mental rotation tasks, half of them come from visual search tasks. There's no difference. Okay? The degree of slowing on these things, which clearly are very different kinds of tasks, and even from a cognitive perspective, you know, very different things must be going on. But from the point of view of aging, the same thing is going on. They're being slowed to exactly the same kind of degree. Those things that we're looking at, we did see that what we had was uniform slowing, but in fact, slowing turns out to be not completely uniform. There seems to be at least one major exception. That is, you can divide tasks into verbal and visuospatial tasks. And are words involved or are words not involved? I mean, it's a straightforward operational definition. Here are this is one which we did a cross-sectional kind of design. So we're looking at people in their 20s, 30s, 40s, 50s, 60s, 70s, 80s. Even by their 30s, people are a little bit slower than they were when they were younger. But you can see that these visuospatial tasks are slowed a little bit more than the verbal tasks, which are these open circles here. 4 different tasks, so that again, even within the verbal domain, we seem to be seeing something uniform that's going on across all these tasks. And again, in the visuospatial domain, 4 different tasks, and they're slowed to the same degree. By the time people get to be in their 50s, they're a little bit slower, but they're especially slower on these visual spatial tasks. By the time they're in the 70s, this difference between verbal and visuospatial has increased even further. This is looking at it in terms of group averages, but let me go back one way. Let's go back. Okay. And one more. Okay. So we can characterize an individual in terms of the slope of that line that measures their slowing. So when we come to this kind of a thing, we can take each individual and give them a verbal slope and a visuospatial slope, so we can measure their verbal slowing and their visuospatial slowing. Then here we can take each individual who's got these 2 data points. This is kind of massive data reduction that's going on, but if you participated in this study, you would have a visuospatial slope value that reflected your visuospatial slowing, your verbal slope, which would be your verbal slowing, and very little going on with the verbal. It is increasing slightly. This is an exponential increase in the degree of slowing in the visuospatial domain. By the time people are in their 70s, 75 or so, there's no overlap anymore between the visuospatial slowing and the verbal slowing. So things are not completely uniform, but there do seem to be at least two major characteristics that you can use to talk about the slowing, one for each of those two domains. We then began to think, well, okay, we're looking at older adults and older individuals, and able to characterize those, the speed with which they can do things across a variety of tasks. Well, maybe we can do this with young adults too. So let's look at individual differences. Here's one of my favorite individuals, and she believes that some people are in fact just generally faster to make decisions, and she certainly is. Here are 4 individuals, kind of somewhat randomly selected. They're we rank everybody in terms of speed, and then we took the 5th, 10th, 55th, 60th. This is out of a study involving 65 different people, 65 young adults, Washington University undergraduates. Some of them, now we're going to plot them against the average for their group. So they're being plotted against their peers. Some of them are generally slower on everything, just like you would see if you were looking at an older adult against the young adult mean, but some of them are faster than average. And again, you see relatively little in terms of strengths and weaknesses, as if you can characterize people as being generally fast, generally slow. This gets really very precise kinds of relationships emerge. Now, if you start averaging, so we took this group of 65 people, we divided it into quartiles, took the slowest 25% and the fastest 25%, plotted it against the average, and you get this kind of a very nice relationship that it's actually, here we've done it it's shown from 2 different studies with 2 different groups of young adults. For one of these, each symbol here represents a different kind of task. Tasks may have multiple conditions that differ in difficulty, just like in the ones that I was talking about before. But in the Hale and Jansen study, I think there are 6 or 7 different tasks that people are being tested on. And it's easier to come up with multiple tasks for the young adults because they don't show this distinction between verbal and visuospatial. So all their data points tend to fall along the line. Vernon and Jensen published a paper in which what they did was they took students who were students at a vocational college, gave them the same tests, the same tasks as university students, and this is again 4 different tasks that they chose, and their data look just like our data. But what's interesting in that case is they also gave their subjects intelligence tests, and not surprisingly, the university students scored higher than the vocational college students did. And this was supportive of the notion that, well, maybe it's the speed at which people can process information that determines intelligence. But although here we're just looking at the group level. If you actually do correlations, you find that there's a significant relationship, but it's not terribly strong. So one of the things we went on to do was say, well, okay, can we find a stronger relationship? And one of the things that people interested in individual differences have kind of focused on recently is working memory, which it's sort of related to like short-term memory, except people not only measure memory span, but they also measure memory span while you're multitasking. How well can you hang on to information if you have to do something else at the same time, which in the real world you often do. And working memory is another thing that older adults have particular kinds of problems with. So we devised a set of working memory tasks, again, to look not only to compare simple short-term memory with working memory, but also to look again for this kind of visuospatial verbal kind of split, to see if there's the same, if that is as important a distinction for working memory as it is for speed of decision making. So in these tasks, okay, here's something that's like a simple short-term memory task, like a digit span task. You get a string of digits, and then you have to report what they were. But in one of the conditions, this is what people would call the first kind of thing sometimes a simple span task, and if you add a secondary task, it's called a complex span task. Okay, so people get a digit they have to remember, but they also have to say what color it is. Okay, this is a very simple kind of thing. If it's red, you say red. If it's white, you say white. But then at the end, you don't have to remember what the colors are, but we want you to still report back the digits. A visuospatial version of that, we put up a little palette. Okay, and so if it's red, you have to reach over and touch that red spot on the palette. And the way that this was done, actually, the positions of the different colors in the palette changed every time a new digit appeared. Okay, so you actually had to look over and see and find the matching color and then touch it, and then at the end report back the digits. Here's a visuospatial version of that kind of thing, where you get X's in a location in a grid, and then you have to mark locations. Although these days we do it with a touch screen, so you just touch the screen where in fact you saw the X's. Again, we can combine that with these same kinds of secondary tasks, so that you're trying to hold on to this information while multitasking. This is what happens with young adults. What you get is same domain interference and no cross-domain interference. That even if you have to do something that is as simple as just name those colors, you're losing about an item and a half off of your memory span. But it's not identifying the color that's involved, because you have to do the same thing in the spatial version, where you have to find the matching color and touch that, and that doesn't affect your memory span at all. And you see an analogous but kind of reverse thing here when it's a spatial memory task. Then naming the color doesn't affect it at all, but having to reach over and touch the matching color again really takes a hit out of your memory span. So now we can give this to young and older adults and compare their performance. This is a new group of young adults, but their data looks pretty much the same. Here, the older adults, you see two things that are interesting. One is that if you just look at a task, you see exactly the same kind of pattern. That is, you're getting something that's really very selective, and interference only when the secondary task is from the same domain. And the older adults generally do not remember as well as the young adults do. But that's, again, particularly true in the visuospatial domain. These numbers are not that different from these numbers. These numbers, however, are way down. So there seems to be some consistency as we go from just looking at the speed of responding to ability to remember things, especially in the presence of interference, in that visuospatial performance is affected much more than verbal performance. But there's no evidence of increased susceptibility to interference in the older adults. They're not being more distracted. There are a variety of ways that cognitive psychologists have tried to explain age differences in working memory, but they really don't hold up. That this kind of a drop is just like this kind of a drop. This kind of a drop is, well, it may be even a little bit smaller, but generally this interference is pretty much the same, regardless of age, but basic memory span is in fact different. This is another way of looking at this susceptibility to interference as a function of age. Here we're looking at a whole lot of tasks to see how general this is. These are 3 different simple verbal span tasks that differ in what the item is, the kind of item is that you're supposed to be remembering, whether it's digits, letters, or words. Here we've added a secondary task and a same domain secondary task, so it's one of these complex verbal things, and the rate of decline is exactly the same. Again, if we look at various spatial memory span tasks, they decline much more rapidly, but it doesn't make any difference whether they're complex or simple. So no evidence of any changes in susceptibility to interference. Now, working memory turns out to be a better predictor of fluid intelligence than speed does. And the question, I guess, for behavior analysts would be, who cares about these things? Well, one reason to care is that with respect to intelligence, what you're really talking about is very simple. That people who are good at some things tend to be good at other things, and people who tend to be poor at one thing tend to be poor at lots of other things. And that's the essence of what's meant by intelligence and why we start invoking that kind of term. And it's maybe the most replicated result in all of psychology. There are all kinds of tests that do it. You can make up your own. It really doesn't matter. You give people a lot of tests, and the same people will be scoring at the top on all of them. And as we wrote in JAB recently, of all places, it really is kind of paradoxical if what we're doing is studying individual behavior, not to study individual differences. After all, it's because of individual differences, in a sense, that we can't just look at group averages. It's because individuals are at least potentially different in important ways. And so in that sense, individual differences are kind of underlying our whole approach to everything about behavior. And it then seems to behoove us to actually take a look at the most fundamental property of individual differences, which is this consistency of performance across different tasks. So we've started looking at this in young adults and in older adults. People often divide intelligence into 2 kinds of categories. Crystallized intelligence, which would be the kinds of things that reflect your background knowledge. You really can't do things very intelligently without knowledge. So that's certainly important. But then the other flavor in which intelligence comes is what's called fluid intelligence, which is really how intelligently you can behave in relatively novel situations. What's interesting is that these two things are very highly correlated. Again, people who have high vocabularies also seem to do better at on memory span tasks, and respond faster. Why should these things be true? Yet learning has been relatively. I guess let me back up just one step, because intelligence tests were originally developed and they're still widely used to predict how people are going to do in an educational setting. And they do a reasonable job of doing that. And if intelligence predict how you do in education, and education is learning, then this is just a correlation. You can obviously turn this thing around, and learning must predict intelligence. So if learning predicts intelligence scores, why haven't people been studying it? And they tried decades ago, and it didn't go very well. They found very weak correlations, much weaker than they got even when they were looking at things like response speed or more recently working memory. Learning correlations with intelligence test scores tend to be around 0.15, although they bounce around a lot. Speed is more like 0.25 across a lot of different studies, and working memory is more like 0.35. And so why study learning when you can study these other things that are better predictors? And that's what they did until Ben Williams, who was referred to in actually several earlier tutorials, developed a different kind of complex learning task. And it kind of grew out of his interest in three-term contingencies as an operant conditioner, although I'm not sure that it really is functionally that analogous. But the important thing is that this task turns out to have a correlation with intelligence test scores, at least in his initial study, of 0.5, which is amazingly high for this kind of research. So we set out to first to try and replicate that, because we wanted to replicate it in young adults. Before you study things in older adults, it's a good idea to have some handle on them in young adults, so that you sort of know what you're comparing age groups on. And in addition, we wanted to get a better idea of how this three-term learning was related to other kinds of things, like in particular working memory, that people had been focused on in this kind of intelligence research. So we got a lot of Washington University undergraduates. Actually, for this kind of research, 60 is not a lot, but that's what we did for our first study. Gave people working memory tasks, these three-term learning tasks, both Ben's original one and a new one that we made up, and the Raven's Advanced Progressive Matrices test, which is the kind of gold standard in fluid intelligence tests. And here's the way Ben's task works. You get a primary word here, lie. You're told which response to make. So press A, and being compliant, you press A, and then you get another word. And now you're supposed to remember this three-term relationship. Lie, a, fan. Okay? We go on now to B. Okay? B, when you press that, it gets you another word. C gets you yet a third word. Okay? So for each of the for this primary word, you have to remember 3 secondary words and what their relationship is to the primary word, whether it's an A word, a B word, or a C word. And then we go on to give you 9 more primary words. So you're ultimately got 10 primary words, 30 secondary words that are related in this very specific way. And we proceed now to go through and test you on all these things, having you type in, okay, lie A. What was that word? All right. It was fan. And if you type in the wrong word, we give you corrective feedback. In addition, we developed another task that has the same kind of structure, in that you're going to get a primary item and a particular response to make, and then it has to be connected to a secondary item. There are going to be 3 secondary patterns that are related to each primary pattern, and we're going to run through all these things and then test you on them, giving you corrective feedback, and then proceed to do this in both cases through 4 different blocks of learning testing. Okay, only the one important thing is this is both not verbal, I mean it's visuospatial, but also it's a recognition test instead of a recall test. So it's really quite different. People get this Raven's Advanced Progressive Matrix test where you get a 3x3 matrix and you have to figure out which one of these things goes in there, which from the different alternatives that are presented below. This is what the correlation matrix looks like from this study. Again, Ben got correlations with the fluid intelligence tests of about 0.5. Well, 0.49 is pretty close. The working memory task, I mean, this is high for a working memory task, but it's definitely at, it's about 0.1 lower than this correlation. A simple spatial memory task, this kind of grid span like the one we showed you before, that does pretty well. Our pattern learning task didn't do very well, but in fact we had really made it too difficult, so we went back and devised another simpler version of it. And now, but kind of encouraged by those results, we decided to now look at the effects of age on this stuff. Got 80 adults between 30 and 80, and tested them on 2 speed tasks, 3 working memory tasks, 3 learning tasks, all of these 3-term learning tasks, and 3 measures of fluid intelligence. We added this kind of thing, which has the same structure, but now you're remembering not patterns but locations. This is the study from which that data that I showed you earlier came from. So you can see the big decreases in speed. These other things are decreasing about the same rate. But what was probably really most important about all this is if we take the average learning score and correlate it with the average score on these fluid intelligence tests, you get a correlation of 0.75. Now, mainly we're probably just improving the accuracy of our measurements by giving more different tests of each kind. But this is an unheard of previously, the high correlation, and this is what that correlation matrix looks like. Again, this is much higher than working memory, which is higher than speed. And with this kind of data now, we can do a path analysis to get at the hypothesis that I mentioned at the very beginning. This kind of notion of a cascade where slowing can affect working memory, can affect learning, can affect fluid intelligence. What you're looking at are partial correlations. Okay, so what this says is that once we control for speed, working memory, and learning performance, age adds absolutely nothing to the prediction of intelligence. That is, these kinds of changes account for all the age-related changes that we see in fluid intelligence. Speed has a relatively weak effect. Three-term learning has a very strong effect. This is at 0.69. It's less than that 0.75 because now we're controlling for the contribution of speed to the prediction. And working memory, its ability to predict is all handled by the three-term learning scores. So working memory contributes nothing unique. So the kind of interpretation that one makes then is that, well, three-term learning must involve working memory, but it involves something else that's important as well. And that's why working memory has no unique contribution to make. But so the question then becomes, well, but why is learning so important for fluid intelligence? Would suggest that there are two kinds of possibilities. One of them is that you're actually learning things as you're taking these intelligence tests. And another is that you're bringing some kind of background knowledge to the tests. Although the fluid intelligence tests are specifically designed to try and minimize that. But nonetheless, because of the way the tests are structured, where they get progressively more difficult, it's almost like you're shaping people up to do these tasks. So it seems reasonable that learning could play an important role. And also, what you're doing is you're learning rules. These problems are solved by figuring out the rules that are represented by the matrix pattern. And these rules recur. They recur in combinations and they recur singly. And so there's lots of ways that learning can be involved in actually performing on these intelligence tests. And so that seems to be a major possibility. It's also possible that in fact, you do bring a fair amount of tacit knowledge not to problem solving to these kinds of things. But one of the things that is appealing about this way of thinking about it is that it may explain better the relationship between fluid and crystallized intelligence. I mean, these two things are very conceptually distinct. They show different kinds of age patterns. Crystallized intelligence tends to remain stable, fluid declines, but they are very highly correlated. Since crystallized intelligence is really just the product of past learning, if fluid intelligence is current learning, how well you could learn in the past should be related to how well you can learn now. And that may explain why these two things are very highly related. I think that I will skip through all this except, let me go back a little bit, to say that what we're currently doing is we're working on training people on working memory to see if we can actually raise their intelligence doing this, and there are indications that we can. This is people's working memory performance going up over training sessions. These are 3 individuals who we've studied so far. In terms of a take-home message or take-home messages from all this, one is that I would encourage behavior analysts to study behavior on cognitive tasks. It's still behavior. There are very interesting, very regular things going on, and you don't need to be put off by this cognitive term. What does it matter if what other people call it? Cognitive behavior is still behavior. Also, I mean, if you're interested in the behavior of individuals, as I said before, you should be studying individual differences, and that includes differences that are associated with age. And with respect to that, let me just skip down to the bottom point here, and I'll tell you a little joke that I actually heard first from the guy who was former director of the National Institute on Aging, and he told a story about an older man who went to see his doctor because his right leg was really giving him problems, and the doctor examined him and was very sympathetic and said, I know this is bothering you, but really, what can you expect? I mean, after all, you're about 80. And the older man said to his doctor, yes, but my left leg is about 82 also, so how come it's doing just fine? Clearly, age is not an explanation for anything. Aging is just the passage of time. It's got to be events that occur in that time period that are responsible for any changes that we see. And the whole goal here is to try and figure out what are those events and how it is that they do result in these age-related changes. And that's it. Thank you.